This wasn't good enough, Matt. Couldn't keep up with the rest.
Good evening. President of AUK, faculty, students, ladies and gentlemen. My name is Ali Sharara, Dean of the College of Art and Science. It's my honor to welcome you all to the lecture series organized by RISE, the Center for Research in Informatics, Science and Engineering, in coordination with the Embassy of the United States of America. Thank you all for coming. Since the beginning of humankind, people have looked up at the night sky and wondered at the frontiers of our knowledge. Most accomplishments that pushed boundaries involve teams of people working together for a common goal. Our tonight's speaker has been at the center of many such collaborative efforts. I'm exceptionally delighted to introduce engineer Nagin Cox, who's a leading scientist at NASA's Jet Propulsion Laboratory. Nagin Cox graduated from Cornell University with a BS in Operations Research and Industrial Engineering and a BA in Psychology, and was commissioned as an officer in the US Air Force. She worked in F-16 aircrew training and received a master's degree in Space Operation Systems Engineering from the Air Force Institute of Technology. In 1993, she joined the Jet Propulsion Laboratory and has since served as a systems engineer and manager on multiple interplanetary robotic missions, including NASA's Galileo mission to Jupiter, the Mars Exploration Rover missions, and the Kepler telescope mission to search for the Earth-like planets around other stars. She's currently a mission lead on the Curiosity rover that landed on Mars in August of 2012 and has been exploring ever since. In her presentation, Dare to Mighty Things, Hitting the Roads on Mars, Engineering Cox will provide insights about the various missions from her extensive experience. I would like to thank all of those who were involved in the organization of this lecture. Please join me in giving Nagin Cox a warm welcoming.
Okay, hello. I am very honored to be here today, and I want to thank AUK and the RISE Center and the president of the university as well as the Dean of Arts and Sciences. I am specifically here tonight at the invitation of the U.S. Embassy, and I really want to thank them for the opportunity to be in Kuwait. This is my first presentation in Kuwait, so I'm looking forward to sharing some stories with y'all about space exploration, about working in teams, and how very international everything we do is when we're exploring space. So this is just a part of what the United States Space Program does. So, since you got that extensive introduction to my background, as I said, I'm an engineer at JPL. I have a background both in arts and sciences as well as in engineering. So what I'm going to do is I'm going to try to talk for about 25, 30 minutes, and then hopefully we'll have time for some questions. But I'd like to start with a video. And so this video is about what happened on the day the Curiosity rover landed. And if we can get that video started in just a second. So we didn't know, we were trying to do something that had never been done before. And we didn't know whether it would work. So what you're going to see is what happened as the data was coming in from Mars, and also the reaction of audiences that were around the United States and the world that were watching as this transpired. And so as you watch this video, see if it's what you think of when you think about science and engineering. It may be a little different than what you're used to.
Things are looking good. force entry interface. At this time, we'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for relative maneuvering in the atmosphere we're about to do. We're standing by for guidance start of guided entry. We're beginning to feel the atmosphere as we go in here. The vehicle just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way into the target. We have seen peak deceleration. That is starting its first anchor burst. Just reporting that we are seeing G's on the order of 11 to 12 per feet. Anchor burst starting. We are now getting telemetry from Moxie. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Fuel 7 has separated where we found the ground command. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for batch separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane started.
Single out, you remain strong.
Touchdown in front of Receive
So that was a very memorable night. And while we're switching back to the slides, so one thing I'd like to point out is a lot of these images are available on the web, but if you please would not film this presentation. That video is available on the web, as well as almost all of the images that I use. Okay, so let's see. Oh yeah, we talked about that. All right, so, and actually in the introduction you guys heard a little bit about my background. So I've wanted to work at JPL since I was 14 years old. And this is basically all I ever wanted to do, is I wanted to work on these robotic missions of exploration. And I've had the chance to work on multiple missions. I got to JPL in 1993. I can't believe it's been like 25 years, but it is just as amazing as when I started. But part of the reason that I wanted to work on robotic missions, so when most people think of the space programs of the world, they tend to think of the International Space Station, of the astronauts, the space shuttle. But there are actually more parts to what the space agencies do. And this is true of all agencies, all the space agencies of the world, that there's also a robotic side to space exploration. And I remember when I was growing up that I actually didn't want to be an astronaut. And the reason for that is when I was growing up, the astronauts were stuck in Earth orbit, right? They weren't going anywhere. If you really wanted to go where no one has gone before, that would be the robots, right? Because the robots are the ones that see places for the very first time. So NASA has multiple, so NASA stands for the National Aeronautics and Space Administration. That's the United States Space Program. And there are centers located throughout the country that all have different areas of expertise. So, for example, when we launch most of our vehicles, it's from the Kennedy Space Center in Florida. The astronauts live and train in Texas. But today we're going to talk about the Jet Propulsion Laboratory in Pasadena, California, which is where I work. So how many of you watched The Big Bang Theory? See, I'm always amazed by that. Wherever I'm speaking, hands go up when I ask that question. So for those of you who are not familiar with The Big Bang Theory, it's a television show about scientists and engineers who work at the California Institute of Technology. So I work at the California Institute of Technology. And I just want to tell you, we're not that bad, right? We're not quite as geeky and nerdy as they make us seem in the television show. But JPL stands for the Jet Propulsion Laboratory. And we are a NASA center that is run for NASA by Caltech. So I work for the California Institute of Technology, but I'm a NASA engineer. So there are about 5,000 people that work at JPL, and we started out as an Army facility back in the 1930s, but when NASA was formed in 1958, we were given the new job of the robotic exploration of the solar system and beyond. So even in the Apollo days, JPL actually launched the first American satellite in 1958, and we continued to send missions to the moon that were robotic. And the goal was to find out what was the moon like, map it, learn about it before we sent people. So before you send robots, you send people. Robotic exploration, human exploration, it all follows the same theme, which is follow the water. Water is necessary for life as we know it. We require water. And so what we are looking for is, was there water elsewhere in the solar system? Is there water now? What about outside our solar system? And should we send astronauts, they'll obviously need water. So it's all about following the water. I'll focus a bit, I've had a chance to work on multiple missions, but I'll talk today about Mars. And so Mars is our nearest planetary neighbor. It's always had a special interest for us. And we try to go to Mars about every 24 months, a window opens up where Mars and the Earth are at their closest point together in their orbit. So that's when it takes less energy, less time to send a spacecraft. So we try to send missions to Mars every 26 months. When we started doing Mars exploration, it was pretty much the United States and the Soviet Union. This was back in the 1960s. It has since become much more global. Now there are many agencies, many countries that are involved: Japan, China, the United States, Soviet Union. India has sent an orbiter to Mars, and in 2020 the UAE is planning to send a mission called HOPE that will join the fleet at Mars. So now it's getting these launch opportunities, like 2020, when we have another rover going, is actually getting quite crowded in terms of, because there's so many different countries that are sending missions to Mars, which is great. It's very international in its exploration. So after a certain point, we have orbiters, those two you see in the top of the frame, that are going around Mars. And so those are orbiters that look at the entire planet, that provide a telecommunications relay. But then after a while, once you've been going to a planet for long enough, you really want to find out what it's like up close, right? It'd be like circling the Earth but never landing on it. Once you've actually landed, you learn a lot more about what the place is like. There have been 4 rovers that have successfully landed on Mars, and I've been privileged to work on 3 of them. The very first one on the left here was Pathfinder, and Pathfinder landed in 1997, and she was no taller than about my knee and probably didn't go much further than this room, right? We were learning, how do you send a vehicle, how do you send a small rover to another planet? How do you deploy it? How do you control it? And then in the center were Spirit and Opportunity Those were in 2003 and 2004, and that was actually the first time I was in that control room that you saw in the video. Only back then they didn't all make us wear matching shirts, right? And so that was the first time that I experienced, what it was like to land on Mars. And then most recently, Curiosity landed in 2012. So there's one slide here for what was 10 years, 5 to 10 years worth of work in building Curiosity. When we design these missions, they take about maybe 5 years at first of kind of inception, thinking what you want to build, what you want to send, and then usually it can take 5 to 7 years to build the spacecraft and fully test it before you send it to Mars. So there was a huge, long process of building these vehicles and getting them ready to go. And usually, by the time you're near the end, in fact, well, not near the end, I'm working on the Mars 2020 rover, which is the next US rover to Mars, and actually we will start, what day is today? We will start our assembly, test, and launch operations. So we're building up the rover. That starts in 10 days. That we will begin actually putting it together all in one piece to get it ready to go to Mars. And so that's when, it's a good thing, the timing of me being able to come now, because soon we'll really get into, we'll get very busy getting the rover ready, and that's when we go to 60-hour, 70-hour, 80-hour, 100-hour weeks, work weeks, in order to get the spacecraft ready to go to Mars. We launched Curiosity in 2011. The day after a major US holiday on Thanksgiving, because we always do these things on holidays, and it takes 7 to 9 months to fly to Mars. So if you're an astronaut going from here to Mars, you would be in your spacecraft for 7 to 9 months. And if there was a scientist up here giving this presentation, this slide always says 7 months later. Right? Like nothing happened in those 7 months. But I am an engineer, and I can tell you we were really busy in those 7 months, getting ready to land on Mars, changing our trajectory to get there. So the scientists who are like our passengers, they always say, and then we got to Mars, right? Except there was a lot of engineering work that went into getting there. Picking a landing site. Where are you going to land? You have one opportunity to land this rover on Mars. You get to pick one place where you're trying to do your mission. And for the 2003 rovers, for Spirit and Opportunity, the mission was to find out, had there ever been liquid water on Mars in the past at the surface? Okay, so that's in the past, we're talking about 3 billion years ago, at the surface, and in liquid form. Was there ever water elsewhere in the solar system? And Spirit and Opportunity, the answer to that was yes. We found out that Mars did have water in the past. So this time we were sending a rover to figure out how long was the water there. Was the water there long enough to have created an environment for life? So imagine that, like tonight when you go home, you take a bucket and you put a bucket of water out on your back porch. And then you go away. If you come back the next day and you look at the bucket of water, it's the same, right? No change, no significant change. But let's say you go away on holiday and you come back in like a month and you go look at that same water. There's going to be stuff growing in it. Right? It's going to start looking kind of icky because it's been there for so long. That's because the water was there long enough to create an environment for life. That's what we're looking for. That's what we're looking for on Mars. We know there was water. Was the water there for long enough to make Mars habitable? And Gale Crater was the location that we picked to go determine that. And that's because Gale Crater, so there's a 5.5 kilometer or 154 kilometer wide crater. In the middle of it is a mountain that from its base, which is underground, is taller than Mount Everest. So the scientists said, if we can go there, we can find out all in one place what Mars was like in the past. So that brings us to the night that you saw in the video. Oh, there's me. I've been asked so many times what it was like to be in that room. And at this moment, we're doing this landing sequence of, we enter the atmosphere. And it takes 6 minutes or so to get from the top of the Martian atmosphere down to the surface. We enter the atmosphere at about 18,000 kilometers per hour. 18,000 kilometers. So that's going really fast. We spent about 4 minutes bleeding off atmosphere, going through the atmosphere and slowing down. And then we use parachutes and rockets to slow us down enough to get to the surface, deploy the rover, land it, and then send the descent stage off to a different part of Mars. And this had never been done before. First time we said to NASA headquarters, we showed that video, something similar, that we showed them, and they were like, no, you're not going to do that. That looks way too risky. Find a different way to do that. We went back, we tried to come up with something that was less crazy than this. We posted a video called the 7 Minutes of Terror, and it went viral with the amount of people that saw it, and we got so many comments back, and all of the comments said basically, that's not going to work, right? That looks way too dangerous. And we knew it had a huge possibility of failing. When Spirit and Opportunity landed on Mars, 2 out of 3 missions to Mars failed. And just a week earlier, a European landing on Mars had failed as well. And then just a couple of years ago, actually it was a year and a half ago, that there was another attempt to land on Mars, and that failed as well. Just because you've done it once doesn't mean it's going to work the next time. These are very risky landings. And so we went back and tried to find a different way to land this rover. But this is what we had to try. If we're ever going to send humans to Mars, we have to learn how to land large things on Mars. And Curiosity is about the size of an SUV, a small SUV. So this is us attempting to land a car on Mars. That's why we look so tense in that earlier picture. We did not know if this was going to work. And it takes anywhere from 5 to 20 minutes for the signal to get from the Earth to Mars and from the Mars to the Earth. That's how far away Mars is. And on that day, landing day, it was about 11 minutes. So we were watching, and that's part of the reason we're literally watching the video, is there's nothing we can do. Everything that was happening on Mars that you saw in the video was autonomous. And we were just waiting to see what happened. Fortunately, everything worked. It was a good day. I was kind of off to the right over there. And again, it's not like, it didn't matter that there were so many cameras in that room. I think there was like an IMAX camera right in front of me. But we weren't thinking about the cameras. It wouldn't have made a difference if there wasn't a single camera in the room. This was a group of people who had literally been working 70, 80-hour work weeks and had been working for a decade to make this happen. And when I show this picture, Steve and Fred always object because this picture is very common in the space arena, and they would say, well, I didn't mean to cry, right? And no one planned to have this level of emotion. In fact, our flight director over on the right, he was the one who, before we landed, we had these entire discussions about how we were going to stay in our seats, how we were going to be very professional and clap politely. Like we always get made fun of by the Johnson Space Center, the astronaut mission control, because we tend to be kind of excitable. And so we said, we're going to be more like JSC, right? We'll sit quietly. Yeah, not so much. And in fact, it was the flight director. He was the one who was jumping up and down. And what you see here is Brian. He's pointing at these pictures in the lower right. Those are thumbnails. Those were images from the rover that told us not only was the rover healthy, that she had landed, but she was safe enough and healthy enough to send these images. It was a group effort that was just so memorable when that happened. And so then President Barack Obama called us from Air Force One. So he was on Air Force One at the time. He called us and said, "Yay!" And we said, "Yay!" And he said, "Thank you for not crashing this, multi-billion-dollar mission," because we had a lot of international partners. And then it was time to get to work. And I remember when this picture came down, and we all walked up to the screens, and we were like, "Wow, that's what." I mean, it never looks the same from the ground as it did from orbit. And so it was time to get to work on Mars, but we did the same thing that everybody else does. The first thing we had to do is we took a selfie. Because the rover has a robotic arm, and at the end of the arm is a camera. So we turned the camera towards us and said, "Hi, Mom," and that's the picture up in the right. Right, and then it was time to get down to business of working on Mars and finding out our objective. So we were carrying, and are still carrying, this huge payload that helps us find out what Mars was like. And Sam and Kevin are our chemistry instruments, right? So Kevin is an X-ray machine, the same kind of X-ray machine as at your doctor, only smaller. And we had to figure out how to get it to Mars. And Sam is like an oven. So if you went home tonight and you walked into your house and you could tell, and you thought there were cookies baking, right? You probably would be able to tell that because you smelled the cookies baking when you came into the house. That is basically the same thing we do on Mars. We use our robotic arm, scoop up some soil, stick it behind us, put it in our oven, and heat it. And then we sniff the vapors. We smell the composition to find out what Mars is like. So we've taken a chemistry lab to Mars. And so, okay, Mars time. So given that the difference in time from Mars, the Earth rotates in 24 hours. So that's our day. The Martian day is 24 hours and 40 minutes because it takes Mars longer to rotate. And so right now, it is 2 p.m. on Mars. So this is a Martian watch. And the reason I have a Mars watch, this is a mechanical watch that has been adjusted to run more slowly so it mimics Mars time. And the reason, I think I'm wearing it in this picture, the reason when we first land on Mars, we spend 90 days on Mars time. And the reason for that is we want to act as if we're living on Mars, so we make the best use of our time. We never know how long these rovers are going to last, and so we need to make the best use of time. So that means I would come into work at 5 p.m. every day, Mars time. And that's because while the rover is sleeping, we figure out what she should do the next day. So we work the Martian night shift. While the rover is sleeping, the humans figure out the plan. But if I want to come into work at 5 p.m. every day, Mars time, we had to come into work 40 minutes later every day. So imagine that you were to come to university at 8 a.m. one day. The next day would be 8:40. The day after that would be 9:20. And the day after that would be 10 a.m. So we were changing one time zone approximately every day. And that was to stay in sync with Mars time, so that we could act as if we are living on Earth, but we're working on Mars. So I never have enough time to talk about this, which is why I actually did a TED Talk on this. It's called What Time Is It on Mars? And I go into a little bit more detail on what it's like to live on Mars time, but I've done it 3 times now, and this is part of what it means to be working on one planet, to live on one planet, but actually work on another. So this is the mission control room for uplink during those 90 sols. And so that 90 sols, we had literally scientists from around the world. I think, let's see, those are the Spaniards in the front. No, the Spaniards are in the second row, the Russians are in the first row, the Italians are in the third row. These science teams are comprised of scientists from literally around the world. There are about 400 of them. And what we're doing is we're all looking at the screen about what, as we're looking at the schedule that we're planning for what Curiosity will do the next day. We communicate with these spacecraft through large antennas that can send signals all the way to Mars from our network, the Deep Space Network. We have antennas in Australia, in Spain, and in Goldstone, California, and this is how we transmit our commands to the rovers. So, the results, so these are some of my favorite pictures from Mars. The one in the center, we went to Mars to find out with Curiosity, was Mars habitable? Was the water there long enough to have created an environment for life? And the answer is yes. If you had been standing in this spot on Mars 3 billion years ago, you could have drunk the water. You would have been, and I say that because the project scientist walked in one day when I was on shift, and he picked up my water bottle, and that's exactly what he said. He said, we're telling the flight team this before we tell the press. And that was if you'd been standing there, you would be standing in basically a rushing river, something that came up to your waist. Mars was once very, very different than it is now. As we've been exploring Mars, we've been there since 2012, and now it's 2018. We have had, things go wrong. We've had some trouble with our wheels. We have not drilled on Mars for a year. A year ago, we started having trouble with the drill. It took us a year. It wouldn't retract, and so we needed to figure out a different way to drill. We came up with another way instead of using the drill, so if you're drilling at home, right, you can, once you get the drill to the wall, you push a button, right, and the drill goes in, right? And we were having trouble with that part of the drill, so we had to figure out a different way to use the drill. We found a way, we drilled for the first time, let's see, what day is today? Sunday. We drilled a week ago on Monday, and I was on shift that day, and we were successful, but it turned out the rock was pretty hard, and so we did it again, and actually it's 2 p.m. now, and I've been checking my phone because we're waiting for data to see if we tried a second time, and it actually happened on Mars about an hour ago. Well, no, it's 2 p.m. on Mars, so it probably happened about 2 hours ago on Mars. So we're waiting for the data to come down to tell us if we have regained the ability to drill on Mars. Things go wrong. There's no astronauts to fix them. We have to find other ways to fix things from here. This is the area we're in Mars right now. Looks a little like Wadi Rum. And also like parts of Arizona. So we're kind of down in the lower hills right now. The mission that I'm working on now, I'll finish up with a couple slides about this and then go on to questions. The 2020 rover, so we know there was water on Mars. We know Mars was once habitable. Now the question is, was there life? And we are very careful before we say that we are a life detection mission. Mars 2020 is the life detection mission. We will be going specifically to look for signatures. We have new landing techniques that we'll be using to try to land more precisely so we can go to different parts of Mars. We actually also have, how many of you guys saw the movie The Martian? Lots of people. So remember the Oxygenator in the movie? So I worked as the deputy instrument engineer on a mission called Moxie. And Moxie is this right here. So in the center, see the big red circle? That's Moxie. Moxie is a prototype. We've been needing to do this for a long time, of an oxygenator. It is designed to take the Martian atmosphere, the carbon dioxide, and pull it apart into oxygen and carbon monoxide. The astronauts will need something to breathe, right? We really need to do this engineering work, and that's a major part of what 2020 will be doing to support human exploration. We will also be taking samples and getting them ready to bring them back to Earth. This is super hard to do. We've gotten to the point, we sent, you know, this giant car to Mars as a chemistry lab. If we're going to look for signs of life, we can do some of that, but we need to bring samples back to the Earth. The samples we brought back from the moon, astronauts were there to pick up the rocks, put them in the capsule, and return them to the Earth. This time we're trying to do this robotically, right? We're trying to take samples, and then we have to actually seal the samples so well that they are safe to bring back to Earth, that there's no possibility of returning an organism that, or something, returning something that could be harmful. So this is what we're working on right now. Never been done before, very hard to do. And then, you know, look at all the steps that have to happen. We have to land safely. We have to go over, get samples. Then we have to keep the samples until another vehicle arrives. We have to give the samples to the other spacecraft, launch the spacecraft back up into the atmosphere of Mars, have it rendezvous with another spacecraft, hand off the samples, and get them back to Earth. That's as hard as it sounds, right? And every one of those pieces have to work. As you can see, in 2020, we are part of the ExoMars is going from ESA, China's sending a rover and an orbiter, and HOPE is the name of the UAE mission. All of these are in support of what we hope is human exploration in about the 2040s or so. That's when NASA would like to go. SpaceX is hoping to send humans sooner, and they're getting a start with that. And you might have seen the launch of the Falcon Heavy that occurred, and it is. And with some of the things they're doing, like this amazing dual, simultaneous landing of the boosters, the biggest obstacle to really getting human presence out into space is having the ability to send payload, to send rockets into space without it being as expensive, which is something that SpaceX is working on. A human mission to Mars is going to be, I took this picture, actually my husband took this picture in Antarctica last year, and if we go to Mars, it's going to be an international mission with a crew of probably 2 to 6 people, and it'll be like our bases in Antarctica. We've had a human presence in Antarctica for 100 years, and no one nation owns Antarctica. It's governed by an international treaty. It's a scientific and research base, which is how we imagine that the visit to Antarctica would be. So these missions that we do are about science and learning about the universe and finding out why Mars is different, but they're also about teams of people doing a job. I remember on the day when this picture came in, that's Curiosity. We have cameras around Mars that are so strong, we can get a picture of the rover. We came unglued when this picture came down. Nobody got any work done. We were all sending this picture around going, look, it's Curiosity, it's our baby. We can see her, right? When you send these missions, you think you're the last person that will ever see this spacecraft when it goes. And then we get these images back of our emissary to Mars. It doesn't feel like a robotic mission when we do these things. It feels like we're there, like we're seeing Mars through our own eyes, through the eyes of these rovers that we have built. I've been at JPL now for 25 years. As a kid, I wanted to work on missions that mattered. What I didn't know is that there was this other component of teams of people that work together to do things that are hard. This is a picture from Apollo 8, a 1968 picture that I remember looking at when I got older and saw this picture, and I thought, this was the first image of the moon, of the Earth from the moon. And I looked at that globe as a little kid and I thought, I see no borders, I see no nations, I see one planet. And that's what made me interested in the space program. There are space agencies throughout the world. This is an international effort. It's one example of solving hard problems. Kuwait has been talking about starting their own space agency. The Egyptians, the UAE, there are many different countries that are interested in becoming spacefaring. And we've got a lot to do, right? The more nations that are spacefaring, the better. There's so much to explore. But space exploration is just one example of problems that we have to solve, right? There's green energy, there's what happens when we don't have, when we need renewable energy, all the oil reserves of the world are going down. There are so many difficult problems to solve. I've been lucky enough to be part of an organization that works on one particular type of problem. But as you look out at what you want to do with your career, think about what it means to work with a group of people to do something hard. Sometimes that takes long hours, it involves failures, but look around you at what Kuwait needs, what the Middle East needs, what the whole world needs. There are problems in the medical field, there are problems to solve and research to be done. I can tell you after 25 years, the thrill does not go away when you work with a group of people to do something that matters. Thank you. So I ran about 5 minutes or 10 minutes over what I was supposed to, but hopefully we still have time for some questions. Yes? We'll have some of this earthwork.
Well, thank you for the amazing and really inspirational talk. Right now in Kuwait, I'm trying to build and design a suborbiter rocket, and I would like to have your opinions on the opportunities of sounding rocket launch in Kuwait, similar to the ones in the Wallops Center, the NASA facility, and what scientific experiments might be suitable for the area in Kuwait and also in the region, the MENA region here.
So that's a great question, which you all heard, which is if in areas that are starting out, you know, what are good ways to start with sounding rockets or CubeSats? There are a number of, there are many different experiments that scientists want to run. The launch opportunities are few. Sounding rockets, CubeSats, usually that are built by universities, built by institutions that are kind of starting out in the space business, do not have any trouble finding questions that scientists need data in order to answer. Starting out with sounding rockets, starting out with CubeSats is one of the most common ways for a space agency or for a space program to kind of get going. But there are other ways in that there was an entrepreneur in Scotland. He used to work for a company in England, Intelsat, that was very large, and he just decided he wanted to live at home, and as opposed to where he was. So he went back to Scotland and he started a company, and was the first and launched the first satellite that Scotland had from his own company, and that was, he took the lessons that he learned from another agency and came back and found again that there was a market for remote sensing and for satellites. So I encourage you to continue with what you're pursuing. The other thing to be aware of is that universities will often start by building instruments. Whenever there's a launch, there are people from around the world, centers, space agency, universities, that compete for the opportunity to send an instrument. Like when India sent their orbiter to Mars, JPL put an instrument on it, but we had to compete for that opportunity. There's a university in Germany who has, over the years, their university has become an expert in the collection, they study the dust particles in space around Jupiter, Saturn, Mars, wherever. And their university has become the experts in how to build instruments that do the study, that study space dust the best, right? And so it can take time for a university to develop that expertise, but it's kind of what is the research interest of your professors, of your institutes, and then it's building up that capability to deliver a sounding rocket, to build a CubeSat. It's easy. One component to remember that is true not just of the space business, but of anything else, is when you have to deliver something on a schedule. If you say you're going to launch a sounding rocket on a specific date, there's the technical aspect, but there's also the managerial aspect of getting it done by that date. We have launch windows to Mars. When we say we're going to launch in 2018, then we have to launch in 2018 or go a whole 2 years later.
Thank you.
So it's an excellent way to start, but I suspect you won't have any trouble finding payloads because there's so many things we need data about.
Okay, so I would like to know what was the biggest obstacle you faced with the 2012 mission and how did you overcome it?
So what was the hardest about 2012? And so our launch date for Curiosity was actually 2009. And we ended up launching in 2011 because we were having troubles with two different things. Some of the entry, descent, landing techniques, we did get those taken care of, but mainly we were having trouble with the motors. So we worked with a lot of partners, and these motors, we had more motors on this rover with its robotic arm and its drill and all the pieces that we needed. And so we had partners that were building the actuators, building the motors. And that was one of the areas that we said, you know what, we have to wait to launch. That was an extremely hard thing to do. It is never easy to go to your professors, to go to your boss, or whoever, and say, I need more time, right? Your PhD is supposed to be in at a certain date. And being able to say, it's not going to be the quality that I wanted it to be, you have to be willing to stand up and do that. That was very hard for us. JPL is typically launched on time. But these things are getting harder and harder to do. We're having the same exact issue right now with launching in 2020, right? We're the sample caching system that's never been done before. It's hard to build a schedule for something you haven't done. But you have to be willing to say, I need more time. You have to be willing to tolerate failure when you're doing things that haven't been done. And so for us, the challenges then were the things that hadn't been done before. And that's the same as we're doing now. The other part of the 2020 rover, it's the same as Curiosity. We're trying to reuse parts of it. But doing things that are hard involve failure and involve being in integrity and saying, this isn't ready, we need more time.
Yes.
Question. My question is about the mission that's going to be in 2020 and a sample that's going to be returned to Earth. How long it will take, okay, for the whole thing until you have the sample back home? This is one thing, and the other thing is that the Elon Musk ambition to go to Mars. Do you see it feasible?
Okay, so the first question was about how long will the sample return mission take? And the answer is, we don't know, but we don't know for political reasons, right? In the sense that NASA gets its funding for a certain amount of time. Maybe, kind of one administration, maybe 4 years, maybe 8 years. And so if we kind of were given the, go ahead, do this whole thing, then we know how long it would take because we know, okay, we have to launch this rover to go get it to, it's got to land and it'll take probably 1 Mars year or 2 Earth years to gather the samples. Then you have to launch a MAV that will land and get the samples. So technically, we know how long it will take. The issue is whether or not there is funding. NASA is less than 1% of the US budget. Right? We have a budget of approximately $18 billion, but that's less than 1% of the national budget. And within that 1%, there are other priorities. right? Like this administration said they'd like us to focus a bit on more on the moon than on Mars. So that could slow things down. We serve and we do things at the pleasure of the taxpayers, right? If the government says, this is the funding that you have, but you have to accomplish these 5 things, then there could be a delay. There can't be too long a delay because we've gathered the samples, right? And right now, one of the goals is we're kind of on this roll where we have the same group of people, and I did not start on Pathfinder, but we literally have people who worked on Pathfinder and then who have worked on all 4 U.S. rovers. My boss, Jennifer Trosper, is one of those 4. And we have a momentum going, and we want to follow that through and complete this engineering problem that has been decades of figuring out why Mars, that Mars was once more like the Earth, and why it has changed, and whether or not there was once life there, and what has happened, and developing and doing that from an engineering perspective. What we don't want to do is stop. We had this problem with Apollo, where we went to the moon, and then by the time we got back to it, a lot of the engineers had retired, and we had to rebuild the knowledge base. So we would like to keep going, but there may be other priorities. And so that's our goal, is how do we keep going at this level that we can finish this task, while those of us who have been working on it for a number of years still have the knowledge. The other question was about Elon Musk and feasibility. So he has shown that Elon Musk has shown that as an entrepreneur, he has a vision for things he wants to see done. That he has sometimes the capability that, since he's commercial and not within the government, to do things in a different way. Just like anybody else who's doing something new, his schedules don't always match up. But when you have the kind of resources that are behind him and the engineering expertise of something like SpaceX, and we trade people, JPL people go to SpaceX, and SpaceX people come to JPL, that it's important I think he has the capability to push forward in his vision. There are things that we need to do, we need to all work together on. Right? It's not, we have navigation expertise that he hasn't built up in his company yet, but it's never a good idea to bet against SpaceX, right? And to get a bet against Elon Musk. He has a goal, and it's entrepreneurship, right? It's if you want to do this, he can definitely make it happen with enough support, and his engineers, are behind him. So I'm personally hoping that he'll get that. Transportation from LA to San Francisco faster. That's another one of his projects that we need.
Yeah, I'm sorry, I think we have time for just one more question.
Okay, thank you. This is Hala Jassar from Physics Department at Kuwait University. Thank you for your presentation. This is really interesting. I have a question. I'm really interested in this Moxie experiment. Yeah, so one thing about Mars is the magnetic field. And I have a question regarding having an atmosphere which is like the Earth atmosphere. Is it like your vision to have this kind of these experiments in a closed environment or open environment? Because the magnetic field was a problem, is that right?
Okay, so Moxie is like a reverse fuel cell. Right? And the idea, part of the technical challenges of Moxie are that we have to, just like a fuel cell, we have to run. It's a very, very thermally challenging experiment because we have to run at a huge temperature in order to do the electrolysis that pulls apart that separates the CO2 into its component pieces. When you ask if it's intended to be a closed system, the answer is yes. On the space station, they run a fuel cell like this, kind of a reverse fuel cell, to give themselves some of the water, but they have humans there to start it up, right, to add a catalyst. One of the problems that we had with Moxie at the beginning is we didn't have such a catalyst to start the process, so we actually had to change the design to introduce that. The magnetic field is not, so Mars has, as I'm sure you know, remnants of a magnetic field. It does not have a global magnetic field, and the Martian atmosphere is like the Earth's atmosphere at about the height of an airliner, right? So it's thin. It's there, but it's thin. And because of that, there really isn't a challenge from the perspective of the magnetic interference, given that it's so weak in the area where we're running the instrument. You're absolutely right that if this was a larger system, but that's not kind of how it's envisioned, right? Once we get it scaled up, basically we'll try to land something like this before the astronauts get there, let it spend 2 years making oxygen, so when the astronauts land, they have the oxygen available for breathing, but more likely for using as a return fuel. Right. And that's what makes the catalyst hard, right? Because you're trying to introduce it, so we've ended up using part of the exhaust to catalyze it, and that all has to be internal. So, okay, I think, let's see, how about one more question? And then afterwards I'll stay around a bit for a few more questions. Yes. So the question was, is it likely, possible, etc., that NASA and SpaceX would work together? And the answer is absolutely, right? I mean, from a JPL perspective, we are thrilled at the way SpaceX is reducing the cost of rockets, because we need a ride, right? We're building rovers and things, and we need a ride to get out to space. So commercial and government can work hand in hand. There are so many things that SpaceX can do because they aren't subject to the same kind of government regulations. On the other hand, JPL has 60 years of experience, which is our 60th birthday this year. So 60 years of experience in launching things into space. So we contribute navigational expertise, and so that's true and of course we're all right next to each other in Los Angeles, relatively. So that's a partnership for JPL and SpaceX is definitely very strong in terms of people and capabilities. For the rest of NASA, SpaceX is definitely hoping to develop a capability for launching NASA payloads, NASA astronauts. It's absolutely from the worker bee, the engineer's perspective, we're all very happy to see this happening because they go hand in hand. Okay, thank you again for the.
Please allow me to thank Engineer Nagin Cox one more time for her impressive talk and inspiration. Thank you all for coming. Thank you for all the organizers, in particular Ms. Dana, Mr. Ha from PR Marketing, the IT, and also people from the American Embassy. Thank you all.